Okay, how's everybody doing? Professor Brian back with another installment of the uh, lecture series for the laboratory experiments. Um, uh, this week's laboratory is going to be the preparation of a calibration curve or standard curve for salicylic acid, and then we're going to use that to actually determine the amount of acetylsalicylic acid in an aspirin tablet. So let's take a look at the experiment. A couple things I wanted to show on the PDF. This PDF, the major outcomes here are we're going to be able to prepare these standard solutions. I'm going to talk a little bit about preparation. We're also going to be able to construct the calibration curve, and I'm going to talk a little bit of theory on Beer's law, which is we haven't covered yet in the classroom, but is very important when we're talking about solution chemistry, particularly on the quantitative scale. We're going to use the calibration curve, Beer's law, and some math to determine molar absorptivity. I'm going to show you how we're going to do that. And then talk about spectrophotometric analysis and the concept of determining how much of something is in solution using light. So the background on aspirin and things you can read. What I wanted to get to was the chemistry. So here we see some structures that kind of look familiar. For those of you all who were in my class, we saw a little bit of macromolecular structures, particularly small scale carbon containing molecules. Here we're dealing with some kind of organic chemistry structures, and you will get to that as you move into general chemistry 2 and then transition into organic chemistry if you are going that way. But acetylsalicylic acid here, which is aspirin, this molecule here, and I don't know why, but the PDF is not showing this as an OH. This should be an OH. It should not be a C, by the way. This molecule is aspirin. This is the drug that is used for people for multiple different purposes. If you introduce aspirin into a basic solution, remember this hydroxide group, we should know that it is basic. If you introduce it to a basic solution, what you end up getting is you get a hydrolyzation reaction, and you create a new molecule. So the chemical reaction takes place. You have an acetate anion as one of the products, and then you have water as another. This salicylate, or this anion here, if you put it into a somewhat acidic solution, you actually end up with this molecule down here on the left. So this molecule here, this is the molecule that is considered salicylic acid, if you will, or the anion of the acid. If you react this molecule in acidic solution, what you do is you actually react it with an iron chloride, iron 3 specifically, iron chloride solution. And that iron chloride solution is actually going to create a transition metal complex. We don't talk about these very much in General Chemistry 1, but in General Chemistry 2, you discuss transition metals and the complexes. But because of the bonding and because of the d orbitals and d electrons in the iron 3+ molecule, we actually see this create a colored complex ion because of those d electrons and the transitions that we've talked about in my class. We have byproducts of acid, hydronium ion, and a byproduct of water, because one of the waters from the complex of iron gets kicked off. Now, the chemistry here is not necessarily one of the major purposes of this lab. This lab is a quantitative analysis lab that is using this chemistry to determine an amount of a molecule that we're interested in. And we're going to be using this reaction here at the bottom to create a standard curve, and that standard curve at multiple different concentrations is what's going to allow us to determine how much of this salicylate is actually in the aspirin tablet that we're using. So we're in a roundabout way, if you will, determining an amount of a chemical indirectly using another chemical, in this case, the salicylic anion, using that chemical based on a standard curve. So I'm going to use the whiteboard in my office to kind of run through what we're doing in the lab and talk about a little theory. Okay. So from a procedural standpoint, we are going to be introducing and using some glassware that we are not familiar with necessarily just yet. We've talked about it. We may have seen some pictures of it, but we will actually be incorporating some new glassware. If you read the procedure very quickly, the procedure says to take salicylic acid. We're taking the chemical in the stock container is chemical reagent grade salicylic acid. And we're going to take a small amount of that solid and we're going to place that in a very small beaker in 5 milliliters of sodium hydroxide. So again, we're going to be mixing with the base as you saw in the procedure. What we are then going to do is we're going to cool this to room temperature. Excuse me real quick. All right. I just wanted to pull up the procedure. So we're gonna heat this up in sodium hydroxide to get it to dissolve. The salicylic acid may not dissolve at room temperature in sodium hydroxide, but just warming it up a little bit will allow us to get it to dissolve. Then we are going to take it off of the hot plate and allow it to kind of cool to room temperature before we dilute it to make our stock. Now, in my course, we just started talking about solutions, molarity, and how we use a stock solution. So we're going to transfer the now dissolved salicylic acid in sodium hydroxide. We're going to transfer that to a 100 milliliter volumetric flask. So a volumetric flask is a flask that has a kind of round bottom. It's flat on the very bottom, rounded on the sides, and then it has a long, narrow neck. On that long, narrow neck, you will see a line, and on that line, that is the volumetric amount that is labeled on each of these flasks. So we're going to be using a 100 milliliter volumetric flask to create our stock. So once we transfer 5 milliliters of the sodium hydroxide and salicylic acid solution to the round, the volumetric flask, we're going to fill using deionized water up to the line. Remember, we're filling it up where the meniscus touches the line, like such. Okay, once we fill that up, we want to use the glass cap, close it, shake it up. Then we have a stock solution at 100 milliliters. Because we know the total amount of solid that was put into the solution and we know the volume of the total solution, we can now know the total molarity. We know the total molarity. Now, what we're doing from there is we want to create a range of solutions that allow us to determine and measure an absorbance so that we can get a standard curve or a calibration curve. And we can use that curve and that slope to determine any unknown using any of these same chemicals. So what we have to do is we have to separate this into 5 different concentrations, and the lab procedure spells it out pretty straightforward that now we're going to move to a smaller volumetric flask. We're going to take 10 mil volumetric flask, and we're going to take from our stock a particular amount in volume, transfer these amounts in volume into each one of the 5 volumetric flasks, from 100 all the way to 500 microliters, and we have pipettes to do that. And we have a conversion factor from drops to microliters, roughly. And in each of these, we're going to also dilute, the same way we did for our stock, dilute up to 10 mils for each of these. We're going to cap these, shake them, make sure that they are mixed properly. Now, for each of these, because again, we knew the concentration of the first stock solution, and we now know how much we put into each of these, and we know the total volume, we can then use M1V1 equals M2V2 to determine the new concentration, or M2, for all of our 5 now concentrations we're using for our standard curve or our calibration curve. And remember, brackets around salicylic acid is equal to molarity. So this is a calculation that we're going to do and is a part of the laboratory manual that you're going to have to do for each of these. So then the question is, well, what do we do with these 5 solutions? Well, this is where we have to talk about Beerlambert Law, and we have to talk about how light interacts with chemical molecules, particularly ones that absorb light in the visible spectrum, or any of the electromagnetic spectrum for that matter. When we see these beautiful colored solutions, if you've taken intro chemistry, you may have seen a very nice blue copper sulfate solution. Any of the transition metals that absorb light, what is actually happening on the physical level? So what I have here is I have a diagram, and this diagram shows you a cuvette, which is a small plastic rectangular prism that holds liquid. If we were to put a liquid inside of that cuvette, and if we were to take a beam of light and we were to shine a beam of light of a given wavelength at that cuvette and then measure how much light was coming out of that cuvette, then we need to talk about some vocabulary terms. The light that is going into the cuvette, into the liquid, through the solution is what we're going to call the incident light, and it is labeled usually as I sub 0 or I naught. And then however much light gets through the solution, however much energy is not absorbed essentially, is considered transmitted light, and we normally label that as just I. The distance from one end of the cuvette to the other that the light must travel through the solution is labeled as small b. We're going to see that later. It's called path length. And so generally speaking, if there is anything in solution, any molecules that absorb at that wavelength, then you should expect a lower amount of transmitted light than your incident light. And this should make sense intuitively. If you have a dark colored solution, getting light through it is going to be difficult. If you think about if you shine a light through some Coca-Cola, it will be tough to see the light on the other side. But if you shine it through some water, you might be able to see that light, right? Because there's nothing in that water necessarily that's absorbing a lot of visible light. So mathematically, how do we look at this? How do we treat these values? So very basic calculation is usually considered transmission. And the transmission is how much light got through. And that is a fractional equation that involves transmitted light divided by incident light. Essentially, what fraction of light got through? That's what transmittance is. Sometimes you will see transmittance presented mathematically as percent transmission, which is 100 multiplied by that same fraction. So 100 times T. For purposes of this course and chemists, we usually like to think of things in terms of absorbance. How much does the molecule absorb? And when we talk about absorbance, we essentially are talking about the logarithm of the inverse of the transmission. So logarithm of 1 over T. Essentially, not how much light got through, but how much light didn't get through. How much got absorbed. So what we see for absorbance is equal to A. We're going to see this equation. And A is equal to logarithm of now I naught over I. So we're looking at the log of the inverse of T. So why is absorbance important? Well, basically speaking, the more light a solution absorbs, or the molecules in a solution absorb, the less light will be transmitted, right? So it's an inverse relationship. When we talk about colored solutions, and if you read the laboratory, you see that our solutions are going to be a dark violet to a light violet, a purplish color. Colored solutions absorb light in a specific wavelength. That's what leads them to have their own color. So a blue absorbs in a certain wavelength, a purple absorbs at a certain wavelength. If we know the wavelength of maximum absorption, and for this laboratory they have told you what that is, you're going to put that into the instrument, and we'll talk a little bit about the instrument when we get in the laboratory. If we know that wavelength, then we can measure the absorbance as a function of concentration. Why is it a function of concentration? Because we have used 5 different concentrations. So we want to measure absorbance at 5 different concentrations. And if we know the wavelength that it absorbs at, we can then plot graphically to create our standard curve absorbance as a function of molarity, and therefore create what is hopefully a linear standard curve if you've done a good job in the laboratory. Now, absorbance is the y-axis, concentration, molarity is the x-axis. You may see a small c on these equations. That is the same as molarity, same as the brackets. Now, if we plot these 5 data points and we get pretty good linear correlation, we can then apply a line of best fit using Excel. And after we apply a line of best fit, we can then look at the equation of that line. So we should be familiar at this point with y equals mx plus b, where m, again, is the slope, x is the variable in the x-axis, and b is the y-intercept, right? Well, when we're talking about absorbance, if we don't have anything in solution that absorbs any of our incident light, at a concentration of 0, we should expect no absorbance. So our y value and our x value at 0 should be the same. What that means is then, if we set b, and again, this is y-intercept b, if we set b equal to 0, then we end up with an equation that is effectively y equals mx with a y-intercept of 0. Now, how does that apply back over here to absorbance? Well, when we're dealing with chemicals, we can convert this equation into what is known as absorbance equation for chemistry, more specifically, which is A equals epsilon, which is Greek letter, epsilon, times B, which is the path length that we spoke about of the cuvette. And the path length of the cuvette is set, is constant. I think it is 1 centimeter for the instruments that we're using, multiplied by concentration C, or multiplied by the molarity. Well, our instrument will be able to give us the value for A on the y-axis. Our instrument is also our mathematical equations and mathematical calculations of molarity will give us concentration. So the slope of this line, y equals mx, is effectively A equals EB as the slope times C. So we can actually determine the molar absorptivity by solving for slope in the equation of our straight line. And once we have y equals mx, once we have created the standard curve, the next step in our experiment is going to be to use that data on the molar absorptivity to then determine an amount of this molecule, salicylic acid, that is in a commercial tablet of aspirin. So we are, again, indirectly going to be able to determine this by creation of a standard curve. But I wanted to just give a quick overview of what we are doing to get people familiar with this. I know this is probably the first quantitative lab that a lot of us are doing, and it's going to involve a lot of work and organization. So I wanted to do a quick recap before you get in the lab. Your instructor will then talk to you about the instrumentation, how to use the instrumentation with the Logger Pro software, and then how to implement that information and how to implement that graph in the solving for the unknown. If you have any questions, you know where to reach me. Feel free to send me an email. Thank you.